Welcome to the flipped classroom. Um, please have the worksheet that accompanies this lecture with you. You are supposed to do that all by yourself. When we come into class, if your answers differ from mine, make a line through them and write the correct answer. I will not penalize you for having the wrong answer. I will penalize you if you do not write the correct answer in. I will also penalize you if you have left questions blank. If you fail to do it, you can do it late for half credit. You ought to write nothing on the worksheet while we go over it in class. I expect you to watch the lecture and fill in the worksheet, and then I will give you partial credit, which is not a good thing, but it's better than a zero. Lectures, also you ought to have your notes out, because frequently definitions or exercises are also there in the notes, and that can save you some effort in writing things that I've already written out for you. Lectures will start with a hook, and on this occasion, at the end of the lecture, I will give you this hook again, and hopefully you will know an answer. The idea of a hook is to intrigue you and get you invested in the lecture, because there is something very engaging and valuable that's going to happen in this lecture. So here's the problem. This person has manufactured cubes that are 1 meter on a side, but when NASA tries to put them into a space that is 10 meters long, they do not fit. And the question is, how come? Did they fail to make them 1 meter on a side? Or did NASA fail to make the cargo bay 10 meters long? What's up with that? Okay. You've already been through, when we went through the scientific method, the fact that as scientists, as physicists, we're going to interact with the real world. We're going to interact with the cosmos, and we're going to expect to learn about it and how it works. And when we interact with the cosmos, we are not going to be satisfied with adjectives like beautiful and big. We need to put numbers on exactly how beautiful it is and exactly how big it is, because mathematics is going to be our essential tool in discovering the relationships and the nature of the universe. And so we are going to put numbers on things. We are going to make measurements, and when we make measurements, we are going to use metric units, otherwise known as the international system or Système International. That we are going to do metric, and so I ask you, what are the metric units of length, mass, and time? Write these on your worksheet, and then I'm going to pull my answer onto the screen, and if you want to add things onto what you wrote, you may. If you want to cross off stuff you wrote and wrote mine instead, you may. This is what you should have had. And I hope that you did it before I drag that on, because, and you don't have to write down all of these, but the point being that there are many metric units, and all of them are good. All of them are good for you to give answers in. All of them are good for me to write problems in. What you cannot do is say that the length is so many inches. We cannot use the English units. From this list of many possible units, we're going to choose some and call them standard SI units, or metric units, or MKS units. From this list, will you please circle the one that is the standard unit? And I would hope that what you circled, and that I hope you did circle before letting the show go on, was meter, kilogram, and second. And the kilogram is the one that I would not be surprised if you got it wrong. Wait a minute, that's got a prefix. That can't be a standard. But we like the size of a kilogram. We call it the MKS system because it is the meter kilogram second system. This one is the one that you probably messed up on. It's the one that I will ask you on the test because there's always the hope you will mess up again, and then I will lick my chops and rub my hands together with glee. We need to deal with these prefixes, the centi and the kilo that we just dealt with. Please fill this in on your worksheet. You making a guess gets a little skin in the game, and then if you're wrong, then there's a little bit of pain, psychic pain, and that will help you to remember, if not have a phobia. So times 10 to the 6th, that's 1,000,000 times. That's mega. Capital M times 10 to the 3rd is kilo. Capital K or a lowercase k. 10 to the minus 2 is centi. Lowercase c, 10 to the minus 3 is milli. Lowercase m, 10 to the minus 6 is micro. And I've run out of m's. So we go to the Greek alphabet and we make a mu. A lot of you need to practice your penmanship. A mu has a long tail out front, and then you make the letter U. Learn to make it right. Some people never master that, and that's like being illiterate, not being able to make your letters. So learn to make it. Here's a little mnemonic to help you. That what you want to do is take this here and bring it around to make a nice round face, and then you put a little triangle nose on here and a little mouth and some whiskers. I think they come in 3s, and then little almond eyes with vertical irises. And this little fella says mu. So there you go. That's how you remember. That's a mu. Get me to cat's ears. Oh, and also I added to the bottom of that list nano, which is 1/100000th and lowercase n. Okay. Moving on. When you make a measurement, if you repeat the measurement to sufficient precision, we do not expect you to get the same answer. But measuring the same thing twice and getting different answers is an error. There are 2 places that error can come from. You can have human error, otherwise known as systemic error, which is because you don't read correctly, or you have bad equipment, or maybe you make an arithmetic error. All of these human or systemic errors, you the human being part of the system. And the way to get rid of those errors is to use good equipment and to use it correctly. We don't like this error. Don't think you're off the hook if you say, well, I did this lab and we got the wrong answer, and I guess it was human error. I gotta say, well, then you did it wrong. You deserve to lose some points. You do it without human error. But even if you do it without systemic error, if you do it to sufficient precision, I expect that you will not get exactly the same answer. And this is the nature of our universe. It does not give us the same appearance when you look at it twice. The universe has changed. It is a random process that gives rise to this. We call it random error or experimental error. And it's unavoidable. It's the way our universe is. So, that being the case, how do you avoid it? How do you get rid of experimental error and make it go away? I want to know your answer. You may be clueless, in which case you want to listen carefully when I go over this in class. But you need to write something. If you leave it blank, I will take off points. Moving on, this failure of the results to be the same is a failure in accuracy. By accuracy, I mean you got what you were supposed to get. Precision, which has very similar meaning. What do you mean, precisely? In English, has a different meaning in science. And so much of what you're going to be doing this year is just mastering vocabulary. That if I ask you, what is the velocity? You need to think about what's the definition of velocity. So knowing definitions is a big part of what we are doing. Right now we're looking at these two. And precision means fineness of measure. Did you measure to the nearest centimeter? Or did you measure to the nearest millimeter? Or did you measure to the nearest tenth of a millimeter? That is precision, has nothing to do with accuracy. I am expecting that every measurement you make will be shown to a tenth of the smallest division on the measuring instrument. So if you write that this is 34.5 and then you give another number there, I understand that that last number you gave was a guess to a tenth of the smallest division, and the measuring instrument you are measuring in is marked to the nearest tenth. This is very awkward, very artificial. You are going to need to remind your lab partners, hey, don't forget to put one more digit so he knows the precision of your measuring instrument. But it is important to me that we always be conscious whenever we make a measurement that there is a limit to how precisely we know it, and if we do arithmetic, a limit to how precisely we know that result as well. In good science, they would write 34.5 and then they would write plus or minus to indicate how precisely they were measuring. That's much better. But when you add two numbers that have different precision, it gets very awkward, and when you multiply them, and I don't want us to deal with all that awkwardness, so this is what we're going to be doing. All measurements given to a tenth of the smallest division. I'm asking you to do that. What is the number that you would put there? How many tenths is that blue line past that 0.5 mark? And I hope that we will become convinced that this is a reasonable thing to do. Stepping away from that precision for a minute, let's go back to accuracy. Accuracy has to do with getting the correct answer, but correct can be just a matter of politically correct. Suppose everybody says that the world is flat, and you say the world is round. Are you inaccurate then? Are you insane? We can skip over this. Suppose you are measuring something that the substance which has never existed before, so there's no place to look up what the answer is supposed to be. How would you evaluate the accuracy of your answer? Again, I want an answer to that. It's very important. And then you can listen to what I have to say in class, but be sure you give an answer. Back to precision. Back to the fact that precision is determined by your measuring instrument, and when you do arithmetic, a calculator should not increase the precision. For addition and subtraction, it is a matter of decimal place. This, like the one we were just doing, is an instrument that is marked 2 tenths, and you are guessing that it is 6 of those tenths past that tenth, 6 hundredths. This one was on a measuring instrument marked to the nearest centimeter, and you were guessing to tenths of a centimeter. When you add them, this is the least precise, and so you can only know this answer to the nearest tenth. Notice the rounding. If you multiply, however, it is a matter of sig figs. And this one has 2 sig figs, this one has 4 sig figs, so this one is the least precise. You only know this to 2 sig figs. Notice the units. Please be very careful to get your units right. In general, in the problems that we do after this unit for the rest of the year, you may assume that they're multiplication problems and do everything in terms of sig figs. But technically, if you are adding, you don't do it in terms of sig figs, you do it in terms of decimal place. And in this unit, you would want to be very careful to distinguish between those two. Quick little comment, these definitions of accuracy and precision that I have given you are for a single measurement. If you have a group of measurements, then there is a different understanding of precision. This is precise because they're all close together. This is imprecise because they're spread apart. That is the definition of precise when you have a group of measurements. I am asking you to parrot back to me the definition of precision for a single measurement. So I have 3 boxes and I measure them, the total length to be 34 centimeters. What sort of a ruler did I measure with? Remember, the last digit is always a guess. I take that 34 and I divide it by 3 to find out how long 1 is, and I get this out of my calculator. That's nonsense. Just because I put it into a calculator did not take something that was measured to the nearest 10 centimeters, and suddenly I know it to the nearest millionth of a centimeter. So what would be the precision here? And stop the show, answer that before we go on, because I'm going to mess up that problem that you did here by pointing out that we need to distinguish that this is not a division where this had 2 sig figs and this has 1, because this is not a measurement. This is a number. I count the 3. I measured the 34. And so that 3 is known to unlimited precision. There were exactly 3 boxes. 3 and no tenths, 3 and no hundredths, 3 and no thousandths boxes, exactly 3 boxes. And so this one would be what would determine the precision to which you knew the answer. Do these. Remember to distinguish between addition and multiplication. Be careful to get the units right and the sig figs right for those. There is a problem that came up in those previous problems that you did, and that is the use of zeros to hold place. If you have the number 100, there is uncertainty about whether those zeros are there to hold place so that this will be in the hundreds place, or if those are actual measurements. Now in chemistry, you had a rule that said if you put a dot, then it makes these be significant. And if you don't put a dot, then the zeros are not significant. But I don't like that. For one thing, how can you, with putting a decimal place, how can you indicate that this one is significant and this one is only holding place? It doesn't work. I don't like it. You use this with me, you will lose points. Instead, we are going to go to scientific notation, where you put the first non-zero digit to the left of the decimal, and then suppose this one is significant and that one is holding place. You only write these digits that are significant here to the right of the decimal, and then you multiply by 10 raised to the appropriate power, so this will mean what it's supposed to mean. It's supposed to mean 100s, so you make this be times 100. Scientific notation. Okay. That's how you ought to be careful about giving your answers on the whenever you do a test, unless you have an answer like 37 and you mean for it to have 2 sig figs, then there's no need for you to write that in scientific notation. But especially when you're dealing with zeros, scientific notation is going to be a necessity. Here is an unfairness. When Mr. Houghton writes a 0, or the book writes a 0, or you find a 0 on a test, it's always significant, unless it's clearly holding place. When you write 100, I don't know. Are those holding place or are they significant? You lose points. When I write 100, it is 3 sig figs. That's the way we play the game. So please write these 3 in scientific notation. Notice these 2 are numbers. This one is data, and so it's got limited precision. Make sure that the product has the correct precision. When you go between dimensions, dimensional, unit analysis or something like that, when you go from feet per hour to inches per minute, what I would suggest you do is multiply by names for 1. I want a name for 1 that gets rid of feet, replaces it with inches, and gets rid of hours and replaces it with minutes. I first figure out what units I want, then I put numbers in here so it's the same quantity on the top and the bottom, a name for 1. If you multiply by 1, it doesn't change how big it is. So this is exactly the same as that, just in different units. In chemistry, you may have liked drawing this grid, and I claim that that's still multiplying by names for 1, at least as I understand the grid. But if that works for you, that's fine. But just make sure you get the right answer. Also, please notice, these are ideas. There are exactly 12 inches in a foot. The precision here is unlimited, and here it's unlimited precision. But this was a measurement. It has only 2 sig figs, and so here you want to make sure you have 2 sig figs. Here's a problem for you to do. Change quarts per pound into gallons per ounce. Here are so you can make your names for 1 correctly. Do that. Get the right sig figs here. What about when the units are squared? Well, rather than trying to have square inches per square foot so that the square feet can go away and be replaced by square inches, I suggest you write it to the first degree. That's how the relationship between inches and feet is defined, and then take that name for 1 and square it, because 1 squared is 1. Please note this 2 distributes, so this is 12 squared inches squared per foot squared, and this is hours squared per 60 squared minutes squared. But you don't try to figure that out. You let your calculator do it for you. You just put a 10 into your calculator, then times 12 squared. This is what your calculator will have, divided by 60 squared. And look at what your calculator gives you. Make sure it has the right sig figs, correct units. Practice. Do it. Be a champion. And back to the hook. And I hope at this point you do have some judgment about what's going on. Why do 10 things 1 meter on a side not fit into a 10-meter long space? The problem was NASA's. Thank you and have a good night.